Okay, the next presentation is from Eyal Ben-Dor from Israel. Eyal, please, your mic is on your computer. Eyal, can you hear me?
Yes, I do hear you. Do you hear me?
Yes.
Okay, so I will just try to share my screen. You see the presentation?
We see your desktop.
Desktop.
Okay, now we can see your presentation. Okay.
All right, good. Okay, so thank you everybody for being awake till my presentation. Actually, my presentation is showing the practical utilization of the UAV in order to find some practical issue and practical mapping of soil parameters. And the idea is to actually go and evaluate the information from hyperspectral sensor and drones to map very high spatial resolution infiltration, water infiltration rate to the soil. This is part of a joint project, and these are the entities that are part of the project. And the introduction of the presentation is actually to deal with soil surface properties, which are controlling water penetration rate to the soil profile. We call it WEIR. And spectral-based analysis in the laboratory demonstrate very good potential to estimate the soil properties in general. So why not to find out if spectral information can predict the water infiltration rate to the soil using, first of all, laboratory, field, and then drones. So the questions we raised up, actually this is part of the PhD thesis of my student Nicholas. And the questions are actually two. Can soil spectroscopy estimate the water infiltration rate values? And then if the drone can carry the hyperspectral sensor, can provide the water infiltration rate map of high spatial resolution scale area. Why water infiltration rate? So water infiltration is strongly affected by soil surface property, and these soil surface property are affected by many soil attributes like calcium carbonate, organic matter, and texture. And all of these attributes actually very nicely depicted by spectroscopy. But this is just to show you the surface when we have crust or sealed. So if you remove the seal, you can find other soil than the sealed soil. So what you have in the first 50 micrometer is not the same as 5 centimeter beneath the seal. And the seal is very important in terms of controlling the infiltration rate of water. So this is just to show what happens if you have runoff, and this seal is blocking the water to penetrate into the soil profile. Lab remote sensing problems. What we have today in the community of soil spectroscopy is that we have many soil spectral libraries all over the world, everybody creating his soil spectral library, but they are all built under a very laboratory condition control. So very strict protocol, and of course, when you take the soil to the laboratory, you definitely destroy the seal that's very important for soil penetration rate. So we assume that the soil spectral library will not provide us a very precise information about the soil crust and therefore about the soil sealing and water penetration rate. So to do the experiment, just for building the model, the spectral model, we collected 114 samples from different areas in the Mediterranean basin, and we measure them with the spectrometer. In this sense, we use ASD, and we did it in field and lab to show or to study if there is any changes between the models that we produce for field and lab, and by that to confirm the hypothesis that the seal is very important for soil, the water infiltration rate of the soil. So in the field, what we did, we measured the infiltration rate by the mini disc infiltrometer, and also we measured the spectral information using the Soil Pro device, which is a small apparatus that is connected to the ASD. And what it does, first of all, it doesn't touch the soil surface. It measures about 30 centimeter diameter the soil, and also it is not affecting by the atmosphere, and you can measure the reflectance at any time of the day. And by this apparatus, you can measure like 100 samples in 4 hours, and it is actually increasing the volume of samples that we can measure at the overpass of one drone or other airborne sensor. Actually, this apparatus is patented, and we already produce it for colleagues, and people are trying, groups are trying to use it in a very positive way. So data acquisition was done as follows. We had like 30 samples from Kibbutz Sde Yoav in Israel, 18 samples from Afeka, 25 samples from Alento, Italy, and 45 samples from different fields in Greece. And we separated these soil samples into two groups. One is clay soil and the other one is sandy soil, because the texture of the soil is very significantly controlling the penetration rate of water. So this is the study site in Tel Aviv. So you see on the left-hand side, you see the non-disturbed and disturbed soil. You can see that they are totally different soil, or totally different probably attribute on the soil surface, and as a result, the penetration rate of water to the soil will be different. These are the soil in Greece. You see different type of soils. And this soil is in Sde Yoav. You see also the crust on the soil surface. And this is the soil in Alento. And what we did, we collected all these soil samples, and we resampled them into the Kubert hyperspectral sensor 185. We run PLSR model to find out what is the possibility to spectrally model the water penetration rate to the soil profile. And then we apply it on the Kubert sensor that was actually flew over the Alento, Italy area. And then we try to map the area for the water penetration rate, and we did some validation tests. So the UAV platform, this is just information where we flew the platform. And this is the setup. You see the Kubert hyperspectral sensor. It's a snapshot. It's not a push broom. So there are some, before was a question about the push broom and snapshot. There are positive things about push broom, and there are positive things about snapshot. but we use the snapshot here, and we calibrate it into to a white panel before taking off. So this is the qubit sensor. It has 135 bands across the Wismir region, and it covers only the 450 to 950 nanometer. So it's the Wismir, and we currently still have no sensor that can cover the entire region that that is not costly as I think Headwall has one model. I'm not sure that the presentation showed the entire region spectral coverage, but anyway, this was on the Wismir. And we also use a gray panel to find out how was the calibration, and if the calibration was not okay, we could use this panel to correct the data using the method that Anna and myself developed, what we call SVC. So all in all, what we can see here, you can see some variation, or the variation between the panel spectral information and the UAV spectral information of the calibration. So you see that it's a pretty good match between them, especially in the dark. And this is not surprising, but also if we measure the ASDS, which is a parameter to find out the difference between the spectral information, we found out that they are quite sufficient, and we proceed with this activity. And here you see the models that we use from the soils. So what you see on the left-hand side is the model that we actually generated from the field, and the right-hand side, the model we generated in the laboratory from the same samples for water infiltration rate. And as you see, our hypothesis was correct, and we confirm it because the field measurement was much better, and they actually mirror the condition in the field. The same thing, this was actually from all samples, for all 114 samples. This is when we separated the sandy groups, and this is when we separate the clay groups. So it was for all of the samples the same pattern. The field information was much better than the laboratory model. And we took this model for the Alento, the clay, because it was more clay soil. We took the clay model, and we measure now. This is actually you see on the right hand side. You see the points of measurement of the measuring spectral information. Also, point of measuring the infiltration rate. And as you see, some of the area is vegetated. So we had to find out what are the bare soil samples. So we did, of course, some NDVI analysis. And by that, we could now implement the model into the soil that were not measured in the field. So first of all, this is the model, and the model is actually implemented into the sensor. And on the left-hand side, you see some interpolation that are using only the samples that measure in the field. And on the right-hand side, we use more samples that were actually predicted by using the model. So we have more samples to do the validation, more samples to do the interpolation, and of course, the right-hand side is much more accurate. And in order to validate this, we went to the field again, and we choose 5 samples. And these 5 samples, we know the water infiltration rate as we measure in the field. And by using the calibration curve of the clay soil, we could find out that the validation was not that bad. We got R square of 0.76. So we were happy with these results, primary results, and we could now go on and do other exercise. We took the samples, the map, the water infiltration rate map, and we resampled it to Sentinel spatial resolution. And on the left-hand side, you see the interpolation of what we did in the field, and on the right hand, how the interpolation get using the predicted information, and we see quite good match between the two. It doesn't say that we can do it in Sentinel-2 because Sentinel-2 has a limited number of bands in the Viesnir sphere, but just for special understanding or special feeling, this shows that we can, if the sensor, satellite sensor or orbital sensor, will have the spectral region of the cuvert of the Viesnir, we can do this exercise as well. There are two sensors today in orbit that carrying this spectral region. One is DASIS from DLR, and the other one is Chris Proba of ESA, but we still cannot get the information and data out of them because it's not public domain data, and especially the DASIS, but the Chris Proba is public domain, but it was not possible for this area to get the data. Anyway, for conclusion, we can say that soil surface reflectance is a broad property to predict WIR remotely. The field-based model showed better results than the base model in all of the than laboratory-based model in all of the soil texture cases. The field spectral-based model was adapted to the calibrated reflectance of the drone and shows, I think, positive results. And the other, I think, conclusion out of this paper is that hyperspectral remote sensing from drone is promising if careful calibration validation is taking place. So thank you very much for your listening. This is a picture of Nicolas and Antonio from Palermo University and myself, and open the floor for questions, and thank you again.
Thank you very much, Eyal, for your presentation, for your study. It's such different approaches. If there are any questions, comments, please.
I have a comment. First of all, thank you so much for the presentation. It is an interesting topic. And I see some potential in this kind of study. Of course, the potential are all in the possibility of predicting hydrological processes over large scale. Starting from the point scale, we wanted to map soil properties with hyperspectral data. This is one of the challenge of Harmonious, but as well as of iAqueduct. The activity so far have been focused only on the comparison with point data, and I wonder if there is an option to validate your infiltration map over a larger scale. And I think that this is possible, probably looking at the integrated result of the outflow of a small catchment and comparing the runoff produced by the subcatchment at the outlet, and compare this outflow with the infiltration rate that is, and from the other side, that the runoff, combining in this case.
You went down.
Yes, I think he'll be back probably.
Salvatore, Salvatore, we missed you. Salvatore.
He probably noticed that and he tried to fix it.
Yes, if you understand
Well,
the comment or question, Eyal, if you can tell his will be back, if you can.
I think it's good
Some
that he will be
suggestion?
back because you know, I can comment on that, but I would like very much to discuss it with Salvatore. So let's wait.
Eyal, meanwhile, I have a question, if
Yes,
I may.
perfect.
So, thank you. It was very informative. I saw the similar results presented by the student, and he's a very talented guy, but it was not that clear. So thank you very much. I got now the full idea of the work. But I wonder if you, so you have in Italy both, right, the UAV, Sentinel, and measurements and ground measurements. And I wonder if you want to try something actually in the opposite direction from Salvatore, saying that maybe you want to do it on a really more precise scale from the satellite. We just published a paper in the remote sensing of the environment of how to reconstruct spectral data using both UAS platform and for Sentinel. So we actually got the Sentinel with very, very high resolution applicable on vineyards. And I wonder if you want to try it for a field scale infiltration maps, because for agriculture, it's the most important, I think. I mean, it's on catchment level, it's very interesting world-wise, but and hydrologically wise, but for a specific applicable science for agriculture, I think on a field level it will be interesting. And Sentinel sometimes is too coarse to find, especially micro effects. So
yeah, you are actually very in consign with our activity, because what before what we did to find out the ceiling effect was to go to a rain simulator. If you remember, we had a rain simulator and we could actually control the drop, the raindrop energy, and by that finding the ceiling effect of the raindrop energy. But this was in the laboratory, and if you would like to go to the field and you have to take with you rain simulator to the field, you can measure 1 point maybe in 1 month. The microinfiltometer is a very good, is a very interesting and very practical tool to go to many points in the field, just for calibration and also for validation, of course. But this was the intention of this research, to do it in high precision way, point by point, point interferometer, point spectroscopy, and then by that to upscale it to other sensors. For instance, the cubert was 5 centimeter pixel size, and if we are going up to Sentinel, it's like 20 meter pixel size. So by that, I mean, by measuring many points, and we can do that, but either by the interferometer and by the Soil Pro, we can get very nice calibration curve, and also very nice validation set of data. So this is the only way I see how we can go to a higher scale. But the only thing is to find out what is the soil texture, and this is you can do by other method, by other model, and also after you do that, to validate or find out validation. This is what we do in remote sensing. So I think, yes, we can, in summary, we can go, we can upscale it to other sensors. And I'm very interested now to go to do it with Prisma, because we have the data of Prisma from Israel. And Prisma is the hyperspectral remote sensing sensor that now in orbit from Italy, and it has 30-meter pixel size. But at the moment, we are now dealing with high spatial resolution and small catchment.
Okay. I have a question.
Salvador is back. Is Salvador back?
He will be back. He is out of electricity. I think maybe.
Ah, wow.
Yeah. Yesterday I was in Rome. All Rome was out of electricity yesterday.
So he told me that he will be back.
And yeah, it was. Everybody went away.
He told me that he will be back, but please, Giuseppe, please.
Eyal, ciao.
Yes. Hi.
Hi. Did you compare the spectral signature derived by using your device, the patented one, with the signature spectral signature derived using the Kubert?
Yes, we did it.
And to do this comparison, did you use the spectral relative spectral response of the sensor, or is not needed in this case?
No, after calibration, you have a reflectance of the area you are dealing with, the pixel or the what we use like to take 10 by 10 pixels, because it's the area of the device, of the Soil Pro device. And, comparing both of them was not bad.
Okay.
It's a visible infrared region, so you don't have much signals or spectral signals. You just have the albedo effect.
Okay, and so I think you just removed the bands that are affected by the influence of atmosphere, if any.
Atmosphere, yeah, but atmosphere is not. Yes, you are right. The atmosphere is one of the things that is interfering the information. But by the calibration to reflectance, you remove it. From radiometric calibration to reflectance calibration or removing the atmosphere attenuations, it's
just this. Okay.
The step, and we did it. And in the end, what you need to do is, of course, to find some validation points that shows the same, more or less the same spectra from the drone and the Soil Pro.
Okay, thank you.
I think, Casper, you should also maybe look for the SVC approach that Eyal showed. I'm really happy that they are using the panels and the cover. It makes a better gradient on the empirical line because you use the same brightness target and you're getting it darker with the density of the net. And so actually the albedo reduction is more controlled rather than shades of gray and black. So, and then another aspect is maybe less, oh no, it's also important for you because it's a spectral reductions. It's actually that you're not adding features, which might be due to the coloring, rather than you just reduce this, or you create the sequence of albedo sequence. So just as a tip for other studies.
Yeah, exactly. Do not use black and white. Just make it available to have grayscale between black and white in order to have a much better empirical line correction or radiometric correction. It was presented by the other presentation today. They use I think, plate, commercial panels. But we use usually we build it ourselves. We take a flat, we paint it white, so the visible region is okay. You find out, of course, that this white color is not having any spectral signal, and then we cover each of the plate by artificial net. Artificial agriculture net by different density. So this is a very cheap method, and it also produces Lambertian reflection more or less. Anna already measured the Lambertian effect of this net, but it's not that significant, so you can use it. And this will do a very good job for correcting the data in the visible in the Vizsnir region.
Okay.
But if you don't mind, I just want to go back and stress the question I had before. My question was that if you want, we can try to really reconstruct. We use the deep CNN, convolutional neural network, in order to train the net and reconstruct images. Actually really precise. It's more or less like punch sharpening, but without any need of additional high resolution images every time. When you have a stabilized end-to-end net, you can introduce just a satellite image and it will reconstruct pseudo or simulated, like almost drawn quality images, not 5 centimeters for sure.
You're speaking about special radiation, special resolution, not about spectral.
Yes,
You're not,
preserving spectral data.
okay.
Okay. By training. So it might be nonlinear relationship, which a net will learn and reconstruct every time it will see the images. So we forced this way Sentinel to be applicable for vineyards, because meanwhile Sentinel, they are useless for 10-meter resolution. You cannot really use them in vineyards. Why Sentinel is important for that specific crop or this agriculture sector? It's because it's a woody plant, and it stresses it remembers the stresses from the period before. So it's not like annual crops which will die if you do not irrigate them or whatever, or if you over irrigate them. Woody species, I assume that Casper is very well familiar with that, will actually reflect their stresses for a longer period, and it will hit you somewhere in the future. So we made, based on the dendrochronology and isotopes in the woody tissues, we really reconstruct the stresses and found them across sentinel images, the specific period when we saw this. The paper presents some vegetation indices because it wasn't our case. The case was to reconstruct better spatial resolution. So this is why I referred and said that maybe sentinel is specifically just too coarse for a field, and your infiltration maps can be more useful if it will be on a spatial resolution in better appearance. Then it will be maybe more informative on a field scale, of course, not regional scale.
But the question is, what happened to the spectral when you do this punch sharpening?
So we test that with spectrometer, with the multispectral imaging, multispectral UAS, and we saw that it preserved very well spectra across Vizsnir. We couldn't monitor SWIR only by spectrometer, but not on drone, on UAS, and but the similarity was really, the ASDS was really close. Of course, after a lot of effort on calibration, but nevertheless, both satellite and drone data should go through calibration, of course, procedure. And but we did it before we started the training. So first we come up with a pretty good set. The back, the really a problem or the drawback of this approach of training, especially convolutional neural networks, is that it's really scene dependent. So if you did it in one region, you cannot simply apply the same network or same coefficients elsewhere. It's really should go through the training procedure. So pre-trained networks, they are less generic or less robust as we would like them to be. But anyhow, if you're interested, for instance, in monitoring on a specific agricultural region, you can do that and get more fine-tuned or better resolution, spatial resolution products.
This is interesting. I will ask Nicholas to contact you, okay? And because he's actually need to upscale this to satellite. This is one of his tasks. So he will contact you, and perhaps we will try to apply this. I have some questions about that, but maybe we will do it over the phone, because I don't like to fatigue the audience.
Thank you very much, Anna. Thank you very much, Eyal. I think Salvatore is back, or no? Maybe not. Okay, I will stop the, any other questions or comments? Not, no. Okay. Salvatore?
Yeah, sorry.
No, it's okay, it's okay.
Yeah. Okay, I'm back.
Okay, if you can repeat your questions, because we lose the last words, the most important words for your questions. So if you kindly repeat your question for Eyal shortly to discuss and.
Okay. The question I was posing is the following. The opportunity to map the infiltration rate at the subcatchment scale is to somehow reconcile filtration process at the point.
Sorry, Salvatore, I think you have two devices, your computer and also your cell phone, if you have a Galaxy S8. If you can stop one of them, because there is a lot of echo here.
Okay, still.
I will mute your, okay.
Let me try.
I mute
Okay,
your
okay.
Galaxy. I mute, you can go on, I think now.
Okay, no. Okay, perfect. No, so what I was saying, we can reconcile with mapping the soil infiltration rate at the catchment scale, the point processes with the basin scale processes. And this is a unique opportunity that can be done, mapping rainfall at the catchment scale, infiltration rate, and computing in this way the runoff spatially, and compare this spatial runoff at the outlet of the catchment. It's something that we didn't try with the experiment of Alento, but it's something that we should try, I think.
Yes, you were missing Anna's comments. She has some method and idea how to upscale the point measurement into larger low resolution, like Sentinel and so forth, and keep the information, the spectral and spatial information. So we can try this and see what we can get if the spectral information is still preserved. And what I said before is that because we have so many, we can measure so many points by both the microinfiltrometer and the Soil Pro. So by that we can actually map the entire catchment in a very precise way. Like if we can measure 100 points over the area, more than, let's say, 50 points that we use, so accuracy will be higher. And of course, you can upscale this and validate. If the validation will show that this works, so I don't think there is any problem. But the problem at the moment is how to upscale it to 20 meter or 30 meter, because in 20 meter and 30 meter, you have mixed pixel problem. So in fact, in 30 meter, you may have, let's say, 1,000 points of measurement that we can do with the infiltrometer. And the question is, of course, you cannot do that. And if one sample within the 30-meter resolution pixel can demonstrate the infiltration in 30 meter, I'm doubt. But you know, all kind of soil spectral information that we did for the 30 meter today in Lancet, or 20 meter for meter for a sentinel. We can do it by validation and calibration of many points. This is my question. My answer. I'm not sure I answered your question, but I think it is possible to do it for the Alento, and we will do it definitely in the future.
No. Partially, yeah, absolutely. This can be done through satellite images, but I think that we can manage it even with the UAS eventually. Of course, it might be difficult to have some validation data, because we may need to have an infiltration rate that is computed immediately before a rainfall event. We'll think about it.
The most important validation is to find out what is the water flow in the end of the catchment, close to the measurement of the soil infiltration rate, because it can be changed by soil moisture, it can be changed by cultivation. Many things can change the soil infiltration rate by liter and so forth. So it's not an easy task, but if this is possible to measure the runoff flow in the catchment, maybe before and after, I think we have the data and compare them to the methods we already generated.
Okay, no. Thank you.
So thank you very much. If there are not any other questions or comments, I will stop the recording.